The broadcast is now starting. All attendees are in listen-only mode.
Hi, and welcome to today's SFPE Perspective Series sponsored webinar, Advanced Smoke Detection Innovations, Addressing Common Challenges. This is Chris Jelenowitz, SFPE's Technical Director, and I will be moderating today's webinar. Before we get started, I'd like to thank our friends at Xtralis, now a Honeywell Company, for sponsoring this webinar. All participants who are SFPE members will receive a certificate of attendance for 1 PDH. To receive a certificate, you must stay online for the entire webinar. Certificates will be sent out via email in about 1 week. Also, we do not provide copies of the speaker's PowerPoint presentations. However, you will be able to access a video of this presentation on the SFPE YouTube channel and website next week. Additionally, you can ask our speaker questions by writing it in the webinar dashboard. Although you can ask a question anytime, we will not be taking questions until the end of the webinar. Today's speaker is Stephen Joseph. Stephen has spent the last 16 of his 28-year career in fire protection, focused on the deployment of fire detection technologies and critical infrastructure. Stephen currently holds a position of Director of Marketing Development for Xtralis, a leading manufacturer and solutions provider of advanced situational awareness detection technologies. Along with his electrical engineering, marketing, and business management background, this exposure has allowed Stephen the opportunity to uniquely consult on fire detection practices for industry, which has included leading corporations across the Americas. Stephen participates with code development committees and is currently a principal technical committee on NFPA 72, Chapter 17, which is initiating devices, NFPA 805 for nuclear, and NFPA 318 for semiconductors. So with that said, welcome, Stephen.
Great. Thank you, Chris, for the introduction, and thank you for everyone for joining in today's session. We'll go ahead and get started. So in today's environment, there are demanding expectations driving fire protection, as a fire can have far-reaching impact on an organization's building, content, and mission. Fire protection strategy is often driven by requirements such as compliance with codes and standards, life safety of occupants, protection of assets, economic loss of assets or function of operations, potential security breaches as threats are heightened during an event, an impact to brand image, and of course, business continuity objectives. So fires can and do happen. Common instigators include electrical systems such as power distribution systems, shorts, overloading, component degradation, and other electrical system malfunction. Mechanical systems such as HVAC systems malfunctioning, and of course HVAC systems aid in the circulation of smoke and gases to other compartments. And there's also the administrative aspect, that is such as bad housekeeping and storage practices, outside contractors not following procedures, and so forth. And of course, the threat of arson. So fire prevention refers to measures taken to prevent fires from becoming destructive, reduce the impact of uncontrolled fire, and save lives and property. It involves the implementation of safety planning practices and drills, and includes education on fire, research, investigation, safety, planning, building construction, safe operations, training, and testing of mitigating systems. Understanding that fires can and do happen, fire protection is a combination of active and passive components intended to minimize the impact of an event. So passive fire protection includes design of building and infrastructures, use of fire restrictive and retardant materials in construction, provisions of isolating fire, firewalls and doors, smoke doors, training, signage, markings, and evacuation of building in case of a fire. Whereas active fire protection includes methods to detect a developing fire and alert emergency personnel, and a means to effectively extinguish a fire. So to minimize a fire risk and its impact, organizations should develop and implement comprehensive and objective fire protection programs Program elements should include fire prevention efforts, building construction improvements, methods to detect and developing fire and alert emergency personnel, and a means to effectively extinguish a fire. Each component is important towards the overall accomplishment of the organization's fire safety goal. It's important for management to outline desired protection objectives during fire and establish a program that addresses these goals. So the fundamental objective of fire protection is, of course, to detect, control, and mitigate the consequences of a fire. Understanding fire development and behavior is beneficial to better planning the protection process. Typically, fire begins as a slow-growth smoldering process, which may last from a few minutes to several hours. It's during this period heat generation increases during light to moderate volumes of smoke. It's during this stage that early detection, either human or automatic, followed by a timely response by qualified fire emergency personnel, can control the fire before significant losses occur. So as the fire reaches the end of the incipient period, there's usually enough heat generation to permit the onset of open visible flames. And once flames have appeared, the fire changes from a relatively minor situation to a serious event with excessive smoke generation, rapid flame, and heat growth. If the building is structurally sound, heat and flames will likely consume all remaining combustibles and then burn out. However, if wall and/or ceiling fire resistance is inadequate, the fire can spread into adjacent spaces and start this process all over again. If the fire remains uncontrolled, complete destruction or burnout of the entire building and contents may result. So as fire growth develops, it becomes progressively more difficult to control, is the message here. The incipient stage of the development of fire offers the best opportunity to control and mitigate consequences of a fire, potentially turning what otherwise would have been a firefighting exercise to nothing more than a maintenance exercise. Automatic fire detection and alarm systems play an essential role in meeting fire protection objectives. With so much at stake, it's imperative that they be applied correctly and are able to perform their intended function. There are a variety of technologies available, and selection is based off an effective response within a particular stage of fire development. There are essentially three major categories of fire detection technologies, the first of which are thermal detectors, which include both fixed temperature and rate of rise detectors. Both of these units are classified as spot-type detectors. A third category of thermal detectors includes linear fixed temperature type devices. Thermal detectors do not function until room temperatures have reached a substantial temperature, at which point the fire is potentially well underway and the damage is growing exponentially. Subsequently, they are not recommended in locations where there is a desire to identify a fire before substantial flames occur. So the second category is flame detectors, which are line-of-sight devices that operate on either an infrared, ultraviolet, or combination principle. Where there is a potential for incipient behavior and the goal is to detect before flames occur, similar to thermal devices, they are not recommended in locations where there is a desire to identify a fire before flames occur. Of course, the third and last category is smoke detectors. As the name implies, these devices are designed to identify it while it's in its smoldering or early stages of development. Common smoke detector technologies include, but are not limited to, spot type, beam type, and air sampling type devices. When properly selected, designed, and installed, a key advantage of smoke detectors is their ability to identify a fire while in the early stages of fire development. And as such, they provide added opportunity for emergency personnel to respond and control the developing condition before severe damage occurs. They are usually the preferred detection method in life safety and high-value applications. Spot-type detectors that are placed along ceilings or high on walls operate on either an ionization or photoelectric principle, with each type having advantages in different applications. And for large open spaces such as atria, frequently used smoke detectors are optical or projected beam type devices. These types of detector generally consist of two components, a transmitter and a receiver, mounted some distance apart. As smoke migrates between the two components, transmission of light becomes obscured or obstructed, which is interpreted as smoke condition. Now, a third type of smoke detector, which is becoming more widely adopted for some of its performance attributes, is air sampling type system. This type of detector consists of two main components: a control unit that houses the detection chamber, an aspiration fan, and operation circuitry. Then, of course, a network of sampling tubes or pipes. And along these pipes are a series of ports that are designed to permit air to enter the tubes and be transported to the detector. Now, under normal conditions, the detector constantly draws an air sample into the detection chamber via the pipe network. The sample is analyzed for the presence of smoke and then returned to atmosphere. The smoke becomes present in the sample, is detected, and an alarm signal transmitted. Spot-type detectors offer key advantages with respect to addressability, electrical supervision, and of course single-line circuit integration. They are simple to engineer into a project and depending on conditions are relatively inexpensive to install. Now, air sampling type detectors having high sensitivity capabilities when properly applied and commissioned are typically the fastest responding automatic detection method. Many IT and communication organizations have standardized on air sampling, but over the years, application has significantly grown outside these verticals as a result of other key attributes the technology has to offer. Attributes such as active performance, physical supervision, centralized performance, and multiple alarm thresholds across a wide sensitivity range have allowed the technology to be applied in a diverse range of applications typically intended to solve particular challenges that would otherwise prevent other forms of detection technologies from being effectively applied. While these are both great technology innovations, there remains challenges for certain applications that neither technology adequately addresses, presenting an opportunity for the development of new innovations. Innovation generally comes about as a result of fulfilling a particular need or set of needs. As the act of innovating, it often starts with users expressing a desirable attribute to solve particular challenges. It's then up to the innovator to interpret those needs as articulated and to anticipate in the unarticulated needs, analyzing what is possible via technology and what is viable in the marketplace. Innovations can take from the form of a completely new method or approach, or take attributes of existing technologies having mutual exclusive attributes, refining and combining those attributes to form a variant of what exists. Innovation is often the role of manufacturers whose goal is generally to grow market share, maintain a competitive edge, and as it relates to fire protection, improve life safety. Essential to the process is voice of the customer, who in our world of fire protection could be the end user, specifying engineer, insurer, HJ, or system integrator. So as it relates to smoke detection, what do we commonly hear? Common challenges when installing smoke detectors include placement of detection points in congested spaces or tight quarters, complexity and cost attributed to installing conduits for spot-type detectors when required, or rigid pipe networks related to air sampling type systems in hard-to-access, congested, or retrofit spaces. Suitability of spot-type detectors in environments having extreme temperatures. And then the disruption to the space aesthetically when installing spot-type detectors or rigid pipe of an air sampling type system where it can't be concealed. Typical challenges as it relates to test, inspection, and maintenance of smoke detectors. Of course, accessibility of detection points in tough areas once installed. This can include floor or ceiling voids when present, congested spaces above or near obstructions, hazardous locations, safety of personnel when working hazardous locations or in hard-to-access areas, risk of business disruption when working above sensitive equipment or processes, and security of information and assets in restricted areas, and of course increased life cycle costs attributed to working in challenging conditions. The desire to have absolute confidence that smoke detection systems will perform their intended function when needed is also critical. While many appreciate the electrical supervision aspects of current technology, there remains questions about functional supervision. That is, the ability to detect obstructions or breaches that would otherwise render the detection system's performance ineffective. So things like covers placed intentionally or unintentionally, or loading of debris over time, which potentially can go unsupervised, preventing smoke from reaching the detector. Or for an air sampling type system having large pipe distribution network, the ability to supervise breach of a single hole. So routine inspections in accordance with codes and standards are intended to identify such breaches, but the desire is to not wait perhaps as long as a year before identifying such conditions. So while these are articulated desires, an example of an unarticulated desire would be that the detection system incorporates preventative measures to routinely and actively keep debris from obstructing smoke. Budgets are continually challenged. Organizations are continually looking for ways to reduce spending. So the messages from the market is loud and clear. There needs to be a solution that can potentially reduce cost, either upfront or over the life of the installation. The market wants a solution that has a long life cycle, is compatible if other parts of the system are replaced or upgraded, and physically is easier to test, inspect, and maintain. Centralized performance is of significant interest, but as well, a system that is compatible across panel models or brands. There's also a desire that smoke detectors be more informative about their operating parameters and the physical environment surrounding them so that personnel can make informed decisions. Things like real-time obscuration levels, event history, maintenance views, multiple alarm levels for stage response were all important. The market additionally desired that this information be easily but securely accessible anywhere, anytime, and that the information and tools for accessing the data be intuitive. So responding to voice of customer, an innovation meeting most of what's been articulated is now available. Let's take a close-up look at this technology. So it was about 18 months ago when this technology was first released, and I had the privilege of introducing this technology via a similar SFPE session. Perhaps some of you were in attendance. While some things remain unchanged and will be a refresher, much has been learned about the technology since its introduction and will be new material. This innovation might be best described as a hybrid solution in that it incorporates addressable attributes of spot type detection coupled with key attributes of air sampling type detection, adding in other essential attributes that sets it apart from anything that's been available before. One key attribute of air sampling type systems is their active performance, meaning the environment is physically and continually drawn into the detection chamber as opposed to passively waiting for smoke to reach the detector. This particular technology incorporates a linear high-capacity vacuum pump, giving it the ability to draw samples across substantially long tube lengths and across environments having pressure differentials. The detector is modular in nature, with each component being field replaceable. Inside, for the main components, we'll find a rotary valve, a pump, a filter, smoke modules, and sample tube inlet, which accepts up to 40 addressable sampling points. So on one device, we have the potential for monitoring up to 40 discrete locations. System components is minimal and fairly straightforward. Main components of the system includes, of course, the detector, an external 24-volt DC power supply, flexible fire-rated microbore tubing with a capacity of up to 40 tubes, each having a maximum capacity of up to 330 feet, and remote sample points available in either flush mount or surface mount configurations. So unlike traditional air sampling type systems, there's no gluing of tubes. Tubes are easily assembled using push-in quick connect fittings for a secure connection. The technology utilizes laser-based light scattering detection principle. Optical protection is provided, eliminating need for incorporating of drift compensation techniques or calibration requirements. This enables the device to provide absolute smoke measurement across the life of its operation. There's a total of 2 detection chambers that are provided within the unit, each supporting up to 20 detection points. This reduces the effect of chamber dilution, aids in rapid detection of smoke and scan sequences, and also provides the ability to set up sensitivity for groups of detection points. There's a total of 4 alarm thresholds that are provided, and those are 2 pre-alarms and 2 alarm thresholds, permitting staged response throughout fire growth development. The system provides 3 possible alarm threshold setting options correlating to sample port sensitivities, and those are high, which is 0.5% obscuration per foot, enhanced, 1.22% obscuration per foot, and standard sensitivity at 2.44% obscuration per foot. Pre-alarms in Fire 2 are set as a percentage of alarm thresholds. Now this simplifies the process of setting up the detector, but yet allows the commissioning technician the flexibility to set thresholds in accordance with project performance objectives. The innovation provides many ways to connect for programming, monitoring, for primary signaling. It supports network connectivity between devices over RS-45. It also incorporates a USB port, which may be used for initial configuration and local maintenance or servicing of the detector using a local PC. It also supports TCP over Ethernet. The Ethernet port may be used for temporary programming or permanent network connection to the detector, and it provides a gateway to other devices on the network. Wi-Fi connectivity is also supported. Wi-Fi allows connection of local client PCs to the detector and provides a gateway to any other device on the network. It also can be used for temporary programming or as a permanent connection to the network. Access over local area network via client PC or PCs can easily be accomplished via wireless or over an Ethernet connection. Access via remote clients from anywhere in the world is also supported. Now, integration to the fire alarm control panel for primary signaling can either be accomplished via a high-level integration with select panel manufacturers or using onboard relays for global alarm and fault reporting by tying in the relays to manufacturer-specific addressable input modules, which then drop onto the panel's signal line circuit. Now, this configuration permits tie-in literally to any manufacturer's fire alarm control panel. So as can be appreciated, there are just a host of ways that we can connect and control and monitor the device or devices. So now let's take a look at the centralized attributes of the technology. Certainly a key advantage, centralized attributes allow for remote and centralized testing and maintenance of the system without ever having to go to individual ports in the field, unless, of course, however, they've been physically damaged and are in need of repair. This offers unprecedented safety and security, requiring only one man and no special tools, lifts, and so forth. Within a couple of minutes, 40 locations can be tested without any disruption to occupants. As a result, as can be appreciated, this offers significant cost savings over the life of the system. The addressable attributes of the technology permits as many as 40 points to be addressed. Addressability is by tube. Expansion modules permit extending this to a total of 120 points. Addressability is ideal for compartmentalized applications such as prison cells, localized detection within fully enclosed equipment cabinets, for instance, and so on, or generally just where there's a location, source location is desired. So in operation, in its monitoring state, smoke and airflow are continually and actively monitored through all ports simultaneously. Again, remember that's up to 40 ports. Upon detection of smoke, global alarms are raised. The unit then enters a smoke scan mode, scanning each tube in groups of 2, remembering that there are 2 detection chambers, until identifying the source by tube or tubes. Another key attribute of the system is its automatic maintenance functionality. The system employs centralized automated testing and maintenance during its normal operation. This ensures that end-to-end system integrity is maintained, including the detector, tubes, and sampling points. Preventive maintenance is not required. During routine site maintenance, simply ensure that there are no faults present at the detector and conduct a centralized smoke test. This is an automatic function that can be set to occur upon a program period, or it can be user initiated. For full end-to-end supervision, the system actively monitors both pump pressure and airflow, which allows for the detection of tube and sampling point breakage and blockage. Any changes in air pressure and flow will create a fault which will pinpoint the affected tube or tubes so that they may be inspected and resolved. Again, this is an automatic function or can be a user-initiated test cycle. Now, informative attributes of the innovation have been carefully implemented to meet needs voiced by the market. The system stores up to 20,000 events in a non-volatile first-in, first-out buffer, providing a host of historical information about the unit's operation, the environment in which it's monitoring, alarms, faults, and user actions. Multiple programmable pre-alarm and alarm thresholds provide an opportunity to monitor fire progression, allowing personnel and emergency responders to stage their response according to conditions or for automatic functions to occur when needed. Control and management tools for both PC and tablets have been developed, allowing users to the power to interact with the system or networks of systems to capture real-time or historic information, or to view maintenance logs and so forth. The tools have been designed to be simple to implement and intuitive to use. So when and where to consider this technology? In areas difficult to access due to obstructions caused by congestion, in areas difficult to access due to ceiling height, or perhaps for retrofit applications where routing of rigid pipe or conduit would otherwise be difficult. In areas secure where access is limited or restricted. In areas subject to EMI RF interference. In areas subject to extreme temperatures, or within fully enclosed equipment cabinets where pinpoint addressability is desired or required, where aesthetics are of concern, where more information about the physical environment is desirable or required. All right, so now that we've had an overview of what drove the need for this innovation and the summary of how it works, let's switch gears and talk specifically about a case study that will give a snapshot of how it's been applied and some lessons learned through its application. So this case study features application of the new innovation in a corporate center for a major high-tech company in tech corner of Silicon Valley. The corporate center is comprised of the 2 4-story buildings that are classified as low-rise B occupancy commercial buildings. Combined, the average number of occupants is upwards towards 2,300. Prior to occupancy, upon inspection, the local AHJ determined fireproofing of the steel support structures to be inadequate. The main concern of the fireproofing material used in the steel structure was whether or not the material used would meet the UL requirements for thermally restrained at elevated temperatures, meaning would the structure remain structurally sound as the steel supports reach temperatures of 1,000 degrees Fahrenheit or greater. At this temperature, thermal expansion begins to occur, leading to support beam failure. As a result of the determination, the AHJ required enhanced fire protection for both structures. The owner was given 3 options by the local authority having jurisdiction. The first option, remove skin and redo fireproofing using adequate material, or the second option, triple the amount of sprinklers in the existing building, or the third option, provide full area smoke detection coverage. Now, the first 2 options were deemed too expensive and posed considerable risk to budgets and occupancy schedules. The third option, full area smoke detection coverage, was assumed to be the lesser of 2 evils, but the owner had objectives they set forth as requirements. So full area detection meant a total of 800 detection points across 2 buildings, each having 4 stories. Installation would have been in accordance with NFPA 72. And then just looking at some of the characteristics of the building, it presented some challenges requiring consideration. So with respect to the open exposed ceiling, with aesthetics in mind, the exposed ceiling throughout both structures would require careful planning and more detail for the installation of devices and material. Obstructions throughout both structures presented challenges for placement of devices near or above the obstruction, then of course accessibility concerns once installed. Obstructions created by building features such as drop ceilings required placement of detection points below. Atria within both structures presented a challenge with respect to placement of detection points and accessibility once installed. Obstructions throughout atriums ruled out use of line-of-sight type technologies. There were also some operational considerations that had to be taken into account, such as access considerations for routine test, inspection, and maintenance in restricted areas once installed. Disruption of workforce when conducting routine test, inspections, or maintenance. And the desire to have supervisory pre-alarms so that personnel could investigate conditions potentially preventing an evacuation. So building configuration coupled with operational considerations formed requirements set forth by the owner. Accordingly, the system had to, at a minimum, be addressable, be accessible without disrupting the workforce, be serviceable without requiring access to restricted areas, provide supervisory pre-alarms for advanced notification of a developing situation, and this requirement tied directly back to limiting disruption, of course. Require minimal servicing, and of course be affordable across life of the installation. And so began the selection process, finding the right tool for the job. Taking into consideration owner criteria, spot type, traditional air sampling type, and the new addressable air sampling type innovations were each investigated. So as we look down each column, matching up suitability in terms of meeting owner criteria, with the exception of CapEx, that is the installation cost, the addressable air sampling detection innovation was a clear choice. The owner chose accordingly, predominantly for its centralized and lower total cost of ownership attributes. Now let's take a close look at the installation. So the installation consisted of a total of 24 addressable air sampling smoke detectors. Placement and spacing of sampling points were in accordance with NFPA 72. Integration via relay to building fire alarm control panel, again, was via relay. Installed since June of 2016 with no reported issues. The installation comprised of 12 addressable air sampling detection units per building with a total of 800 detection points between the two buildings. It had a total of 3 addressable air sampling detection units per floor centrally located within designated zones with tube distribution in mind. Here's what the installation of the sampling point with microbore tubing on an exposed ceiling looked like. And from the installer's perspective, the surface mount sampling points were easy to install using the combination of all thread and disc mounts. And here's another exposed ceiling installation example. And again, from the installer's perspective, tubing was easy to support with J-hooks, circle hooks, and keep tidy using Velcro straps. Here's an example showing routing of flexible microbore tubing at the ceiling. And again, from the installer's perspective, because of the exposed ceiling, all the tubing had to be run in a manner that looked as professional as possible, but this would have been true for running wire. An installation below a T-bar ceiling tile using a flush mount sampling point. And again, from the installer's perspective, mounting of the sampling point to the drop ceiling was easier than using traditional spot detectors, which would have required junction boxes and support straps to the hard deck. And here's an example of installation near or above obstructions. Again, from the installer's perspective, installation near or above obstructions was possible due to centralized test and maintenance capabilities of the system. Here's an installation example of a sample port located in a cramped quarter where it would have otherwise been difficult to install a junction box in a traditional device. Again, from the installer's perspective, due to their size, remote sampling points ports could easily be placed where traditional detection could not reside. And here's an installation example below a ceiling obstruction. Again, from the installer's perspective, detection below obstruction was easily accomplished due to flexibility of microbore tubing. Flush mount sampling points were easy to mount and discrete. Just a little bit more feedback from the installing contractor. So working with the new technology required a learning curve, but once we got a handle on it, it was pretty straightforward. Tubing was much like installing Cat5 cabling, simple to run, but took more planning than running an SLC, that is single line circuit. Relay integration resulted in higher labor and material cost. High-level integration would be a great benefit. Installation of tubing on exposed ceilings required more attention to detail for aesthetic purposes. And some additional installer feedback with respect to centralized attributes. Centralized accessibility for testing and maintenance is a game changer, will significantly reduce cost. And from the owner's perspective, installation had been trouble-free from day one, 6 months running. Disruption of our workforce and access to secure areas were significant concerns for us. The centralized features of the technology eliminates both concerns. Installation was a bit pricey as compared to other technology options, but we expect to see a 30% savings over the life of the installation due to the centralized features of the technology. All right, so in closing, there are a variety of smoke detection technology solutions available. Each have their respective attributes and are ideally suited for applications in which they set out to target. New innovations set out to respond to a set of particular needs that haven't been adequately addressed within current technologies. New innovations, such as the one presented today, arm the industry with additional set of tools, helping overcome existing challenges and potentially new challenges that haven't been yet realized. As applications continue, we're recognizing new ways to apply this technologies in areas that haven't been thought possible. We're also learning some lessons learned that ultimately will allow us an opportunity to refine the innovations. So it was our intent for this session to expose and broaden your awareness of solutions made possible through innovation. I hope I've met that intent. And again, thank you for attending. Chris, back over to you.
All right, Stephen. Hey, thank you very much for a really nice presentation. We do have some time for questions, and I am getting a lot of questions up at the board now. So I'm going to try to get to as many as possible. If you would like to ask a question, feel free to go to your dashboard and send it over to us. And Stephen, I think the first couple areas I'm going to hit on are related to applications. In your case study, you alluded to atriums, and it seems like that would be a great application given the fact that I think everybody who's on the line has seen somebody try to install a spot smoke detector 75 feet up in the ceiling where you can't access this. But can you elaborate a little bit more, or maybe on your case study or other times you dealt with the atrium application?
Yeah, so I mean, the atrium was a unique application in that, ordinarily you could find other ways to serve that type of space using line of sight type devices, which are certainly a consideration, but those as well have their own challenges with respect to accessibility, still having to have access to the device, and then of course any of the building conditions that might influence their behavior. But there are new technologies that set out to do away with some of those challenges, but still, again, back to the idea that we have to get to those devices. And so, this technology served very well in this application. Number one, because there's quite a few obstructions, as one could expect, perhaps, from seasonal decorations or other building features or functions that might occur where it could interrupt line of sight type devices. This proved beneficial with respect that, the ports could easily be placed, concealed, not deter from the aesthetics, and as well the remote capabilities of the system in terms of centralized test and inspection were beneficial.
Okay, great. And in the other application, we received a question, well, a few more, but one is tunnels. Have you seen the air sampling system used in a tunnel before?
Yes, absolutely. We have a number of applications in tunnels. We have very specific products, a variety of products that best handle the types of conditions that the detectors and sample points are exposed to, and certainly reach out to us because we have a lot of experience on that subject and are seeing a growing demand for application of these types of technologies, air sampling type technologies in tunnel.
Okay, then the other area is dirty atmospheres. The example or question included a waste handling facility with a tipping floor with high ceilings. Is that an issue that you need to be looking at?
I'm sorry, I don't understand the question.
Well, dirty atmospheres where there's a lot of dirt in the air, maybe where they were handling waste, solid waste, and there's a lot of dust and stuff like that.
Sure, yeah, and really that's a key advantage of the air sampling type detection technologies, in that the installation can be engineered such that we can deal with a lot of the environmental conditions that the detector or sample ports would be exposed to, and of course having a wide sensitivity range and a number of our product portfolios or air sampling type detection technologies which permit a wide sensitivity range and programmable set points to where you can set those thresholds above higher ambient conditions, allows it to operate reliably, coupled with careful engineering to overcome challenges such as condensation, dust and debris. And again, one of the key advantages of this new innovation is, of course, that function in which it self-cleans itself, which is advantageous where there is a higher level of ambient contaminant that it could be exposed to. But again, air sampling in general, and again we have a variety of different technologies available in the marketplace for air sampling type systems that deal very well with harsh environments.
Great. And we also had a lot of questions about testing these systems. Specifically, could you just review a test protocol? One of the questions that came up was, well, in your slide you showed them testing at the unit itself, but other AHJs may require you go to the end of the line and test it. Is this something we should be doing? And what about testing for supervision and things like that? So I just threw a whole bunch of stuff out there, I know, but maybe review the test protocol and how you recommend these be tested.
Well,
some of the issues you've seen in the field that have come up, maybe because people really didn't understand how these systems worked or not work.
Sure, appreciate that, and I appreciate the questions too, because it is relatively a new concept with respect to being able to test at a centralized location, and of course the questions then come with respect to supervision and how do you know that that port at the end of the tube is actually doing its job in terms of transporting smoke and so forth. And so again, the idea is as you listed this product and tested this product such that the intent is to test at the detector as opposed to in the field. And so what we're essentially doing at the detector itself, as you can see in this illustration here that we've animated, is you have a couple of test points at the side of the detector, and then you put this detector in a test mode such that it then very specifically tests the detection chamber for measurement of smoke, which at that point you're then physically and functionally testing the detection chamber in terms of ensuring that it sees smoke and provides its alarm points in response to smoke. So with that, we've then fully tested the detection chamber, and so then that leaves to question the integrity of the tubes. And as we touched on, the idea that the tubes are fully supervised, so I find that particular slide here, the idea that we're continually monitoring the tubes for blockage and breakage, and not just the tubes, but the sampling ports connected to them. So with that, we have full supervision, and again, functional supervision, end-to-end functional supervision, so not just electrical supervision of the unit itself, but as well physical supervision of the tubing. So if there's a breakage or blockage of the tube, or disconnection of a sample point, or something that impaired the sample point and the tubing back to the detector, we're supervising that continually. So we know that that part of it's functional and tested, and in conjunction with testing the smoke detection chamber at the detection unit itself, we literally have accomplished full test of the system, and that's, I guess, the confidence in that regards. So, I mean, there's a lot of questions that come up in that respect, again, because it's a fairly new concept, but I think we've proven through the supervision of the system and the capabilities of the system that that's entirely practical and effective.
Okay, great. We're talking with Steve and Joseph from Xtralis about smoke detection innovation, and I'm going to field a few more questions out to you. A lot of questions also about the tubing itself. Is this something that's included with the system, or do you purchase this tubing separately?
Yeah, we supplied tubing, and the tubing, again, it's micro bore tubing. It's either 4 to 6 millimeter tubing, and it's fire rated tubing, and it's unique in that it's pre-printed in accordance with NFPA 72. Do not disturb smoke detection. So there's that, labeling of the tubing itself. But then as well is it's unique in that it offers a unique serial number per tube, so the tubes can be identified. Length markers on the tube, such that as you roll out the tube, you have precise measurement of tube, an easy reference point to know how much tubing you've got. So it's something that we supply, and it's easy to work with, and again, because of its size, and as you saw from one of the notes from the installer, it's a lot like working with Cat5 cabling in terms of routing and supporting and so forth.
So then, is it easy to cut the tubing, for installation? Do you want to fit it in a certain location?
Yeah, exactly right. I mean, you have to ensure that you get a nice flush cut on the tubing, but it's easy to work with, and as compared to traditional air sampling type systems, which use rigid CPVC, for instance, where you've got glue and you've got fittings, and the assembly has to be carefully planned in that respect. This is unique in that it's just literally, flexible tubing that's, measured to length, cut, and connected via push connect fittings to sample points and the detector.
Okay, and how about the straps for the tubing? I think you mentioned maybe Velcro straps. Do they need to have any kind of special plenum rating when you're working above ceilings? And is there any requirements that, or is that something that also comes with the system?
Yeah, no, that doesn't come with the system. That was just an installer's choice in their particular application, and that the idea is that they wanted to keep it tidy because of the open ceiling structure. And as you can appreciate from this picture, whether it was wiring or tubing, they would have had some consideration for. I think there's a picture here where we actually would have seen wiring also being supported and tied. Their choice of Velcro straps was just their choice. It could have literally have been any material that kept the tubing together, as it's run in bundles. And so again, it's not anything that is supplied by the manufacturer. It's a variety of different choices that might be available, and certainly if there's a plenum consideration, plenum material should be used for supporting and strapping the tubing to hold it together.
Sure, and does this tubing have any minimum bend radius or flexibility?
Well, it certainly does. Off the top of my head, I don't have that particular bend radius, but it's something that we do have, and guidance is provided with respect to its, the bend radius. As you can see from some of these pictures, as we look at these pictures here, you can see the tubing being coiled, in a pretty tight coil, so it does have quite a bit of capability to coil, which would, then suggest that it has a pretty tight bend radius. But to tell you very specifically what that bend radius is, I don't know off the top of my head, but it's certainly something we can follow up with if questions were submitted to us.
Sure. And then what about the anticipated lifespan for this tubing?
Yeah, so it's nothing that immediately jumps out at me in terms of it having a shelf life of any type that would, there would be degradation or failure of the tubing over time. And again, that's something I think we could follow up with more technical information with respect to the tubing material.
Sure. And then the other range of questions I'm getting is, how do you identify where the alarm's coming from? And, how does the zoning work with so that when the fire department arrives, is there a way to enunciate it to a specific location so the fire department needs to respond or the maintenance needs to go to respond to?
Right. So that's a good question, and of course, the fact is that as we suggest and have talked about, the device is capable of identifying the individual tube carrying smoke. And that's one of the key advantages of the system in that regards. And in terms of the relays on board the detector itself, as I mentioned, there's global relays. There's a total of 7 of them for the alarm thresholds, the pre-alarm and the alarm thresholds, and of course the fault relays. And again, those are considered global alarms and not necessarily tube identification points. And there's what we refer to as a stack module, or an additional module that ties into the device, which is literally a relay enclosure box that then houses the addressable input modules and as well the relays for connectivity to other systems for reporting the individual tube. So individual tube identification comes as a result of that relay connectivity through a separate module. And as I mentioned, there are some manufacturer panels that are integrating high-level communications from our device to their device, and the idea then is that you eliminate that form of connectivity. Now, as more and more manufacturers start to incorporate this, we'll see the simplicity of that information being transmitted intelligently over a high-level integration. As it stands now, where we do not have that high-level capability with particular manufacturers, the choice then is to bring in that information via, as I mentioned, this additional relay stack module.
Great, and then we're also receiving a couple questions about, the age J out there. They might not be familiar with this type of system as they would others. How do you find acceptance of these type of systems, whether it's design, construction, or even acceptance at the acceptance test phase?
Yeah, well, of course it is UL listed, and but there still is that uncertainty as to really what it is, and that's on the part of the manufacturers to broaden the awareness and the education of these types of technologies and their capabilities, and as well as how to inspect them, how to approve them, and so forth. So from a manufacturer's perspective, a lot of education, but we're finding that it's being widely accepted and appreciated for its capabilities. But the education continues, hence sessions such as what we're doing today.
Great. I think we're getting a lot, Stephen. I think we're getting a lot of good questions here. I'm enjoying it. At least the next question I have is about the spacing of sampling points. Is that consistent with what we would see with a spot type detector, or is there different type of spacing requirements?
No, exactly right. I mean, that's exactly what it is. Each port, of course, within a base 72 is of an air sample test system is, installed as purpose considered as a spot type detector in terms of placement and spacing. And, in absence of any, performance-based requirements or objectives, it's spaced in accordance with NFPA 72.
Great. And then I guess the other question that we're receiving a lot of questions about are cost. How do you compare this cost with your average spot type detection?
Yeah, and I'll go back to, what I said in terms of, some of the feedback that we've gotten from the case study is that, as we saw, the owner's response was, was a bit pricey as compared to other detection solutions, but offered a 30% savings over the life of the system. Of course, from an installation perspective, it depends. I mean, there's so many variables depending what the conditions are that we're up against and how many points we're, replacing or not replacing, excuse me, we're talking about in terms of capacity of the system being utilized. It can either be, equivalent or much more expensive, or in some cases less expensive than other detection solutions. The thing is about it is there's just a variety of variables that can influence that. But as we think in terms of the case study that was presented, it being more expensive up front, again, the real saving factor in that regards was the life cycle aspect of it. Again, not having to get to 800 detection points at any given time to test, inspect, maintain, or what have you. The ability to just get to 24 devices to do your testing as opposed to 800 of them was a huge saving factor in this particular case. So again, without taking a particular scenario, it would be hard to say, but certainly we could look at that as the market has particular questions and inquires, looking at the very specific scenario. It's easy then at that point to make some determination as to whether it would be less expensive, more expensive, or what that total cost of ownership aspect might look like.
Sure, great. I don't think we were looking for any definite budget numbers, so I think that's great. And then once again, I think we had an earlier slide, but maybe some people missed it, about the maximum tube length.
Right. Okay, so finding that slide here. The maximum tube length, I'm going to just rattle it off here. It's a total of 330 feet is the maximum tube length. And that could be a combination of 40 tubes, each at 330 feet. So at that point, you can appreciate the capacity of the system in that regards. A lot of flexibility. Of course, as you plan your installation, as we're talking about the particular installation scenario that we were highlighting or featuring for the case study, planning of the zones such that you have distributed tube runs, but you try to centralize your detector such that you reduce the overall length of tubing where you can.
Okay, Stephen, I think this is going to be our final question because we are getting to that point where it's time to end, unfortunately. But the final question I'm going to ask, and I think you mentioned that very early about debris. I know when we're looking at a spot-type smoke detector, of course, you want to worry about the smoke detector getting dirty or debris or things like that. But is the air sampling, is that more susceptible to dust, debris, or things like that? And how do we watch out for that when we're, once these systems are in service?
Yeah, of course, the detector deals with it with respect that, with an air sampling type system, there's generally a filter in place before the detection chamber such that we can capture a lot of that debris as opposed to bringing that debris into the detection chamber, which is ideal. And then, of course, with the supervision of the tubing such that we can identify where potentially debris may have caused a restriction in the airflow such that we generate flow faults in that regards. But one of the key advantages that we've been touching on with this technology, and that was voiced as part of that voice of customer, was the ability for the system to have the capabilities of self-cleaning itself from debris of buildup. And so again, I think it was this particular illustration here where at a high velocity tube by tube, the system routinely on a program period cycles through each of the tubes and performs, and it's from its sense, a purging of the tubing. Now, it does in groups of two, so it's a rather rapid process such that it goes through each tube and ensures that it tries to clear itself from debris. So, which is kind of a unique aspect of the system in that it's self-cleaning. There are ways to accomplish that on a traditional air sampling system, but that's usually an after-the-fact thing where you're adding in, perhaps a connection point and solenoid for compressed air for self-cleaning the system, or simplicity of connecting a shop vac or some other means of cleaning out the tubing. But the fact is, this detection technology automatically does that by way of its operation.
All right. Hey, Stephen. Hey, thanks a lot again, and our friends from Xtralis. I think this was a great presentation to learn more about, some of the innovations that are going on out there at Xtralis. And once again, I appreciate your time, Stephen. And I also want to thank everybody who participated in today's webinar. I hope you have a great day. Thank you very much.
Thank you.